All right, this is our final question for the 2019 AS Paper 1 from AQA for Physics. And we are almost done here. And this is mostly a knowledge-based question. A little bit of maths, but it's mostly just you got to know this stuff. So what is meant by an antiparticle? So there's two things that you would have to mention, and look at that, it's worth 2 marks. So the two things you have to mention, it has the same mass or rest energy. But opposite charge. In other words, the antiparticle for an electron will have the same mass as an electron, but it will be positive, whereas the antiparticle for a proton is going to have the same mass, however, it will be negative. Okay, now this leads into question 2. Complete the names. Well, for a proton, it's really easy, very creatively named. Antiproton. And an electron actually has a better name, a positron, or an anti-electron. Quite frankly, I'd love it if the protons were called negatrons, but they're really not. Can't have everything. So, apparently the exam board does not like anti-electron for positrons. But that's just the way it is. All right, particles of antihydrogen can be made by pair production. Calculate the total minimum energy in joules needed to produce the particles in one atom of antihydrogen. So, what we're going to be doing then is we need to look at, well, how much energy is there in a antihydrogen molecule. So, well, what is that made of? Well, it's made of one antiproton and one positron. So we need to look at the rest energy of a proton and the rest energy of an electron, because those will be the same values for the protons, or for the positrons and the antiprotons. So our rest energy is equal to, so 0.510999 plus 938.257. So these are right from the data sheet. This is in mega electron volts. So what you need to do then is add these together. Remember, you have to use this many significant figures because the differences in some of them are so small. They really want you to they're giving you 6 significant figures on the formula sheet. Use 6 significant figures while you are doing your calculations. So adding that up, and I get 9.38. Oh, why did I do 9.38? 938. .768. So sticking with the correct number of significant figures. Okay, and that's again mega electron volts. Well, that's my answer in joules. So the energy in joules will be 9.38. Oh, I did it again. 938.768 times 10 to the 6 times 1.6 times 10 to the minus 19. That's the right value, isn't it? It's the elemental charge. Yes, 1.6 times 10 to the minus 19. Which, okay, math this out. Really is not liking my 9s today. All right, 1.5 times 10 to the minus 10. And I know I just harped on and on and on about significant figures, but this is enough significant figures when for our answer. It's just that when we're doing our calculations, they want to see the significant figures for the when it's in mega electron volts. Okay, that's the minimum amount of energy. That's the energy that has the minimum amount of energy that we would need to make these particles. Now, in reality, you actually need double that because it is pair production for these here. So when you make an antiproton, you are making a proton at the same time. So that energy has to come from somewhere. It is technically double in reality. However, you know, the mass energy here, that's the minimum mass energy. The reason it has to be double, you need pair production, is conservation of charge. Okay, if you're making a positive, you have to make a negative at the same time. You can't just get charge from nowhere. So yeah, that's pretty much it. Last thing, line emission spectra for hydrogen and anti-hydrogen compound. Explain how line emission spectra are produced. Okay, so a few things that we have to talk about here. We have to talk about the fact that electrons in an atom exist at discrete energy levels. Okay, so right, we know that in these shells we can have an electron in the first shell, we can have an electron in the second shell, but there is no such thing as a first and a half shell. Okay, and electrons just, they do not exist there. They tunnel from one shell to another. Okay, they're in that shell or they're in this shell. They're never in between that shell. Okay, so that when an excited electron drops a shell, sorry, I'm going to call it an energy level. A photon is emitted. Okay? Okay? And then because it's a discrete energy level, and so it's a discrete transition, so if something goes from the second shell to the first shell, it's a fixed amount of energy, which means that that particular photon will have a discrete amount of energy, which means it has a discrete frequency. Okay, so it has a very specific frequency. It's one line on that emission spectra. Okay, so you have to have that idea of a discrete frequency. Okay, related to the energy level. Okay, so that's what we're looking for with a question like this. There are a few other points that we could have in there that I haven't explicitly written down, but I have talked about them. You could talk about the linking the formula for energy, frequency, and wavelength or wavelength, so that you can see that if you got a fixed amount of energy, you've got a fixed frequency, so you're going to get one line. Fun fact: the antihydrogen that we have created in labs, we've been able to test their line emission spectrum, and it is identical. It is indistinguishable from hydrogen. So actually, if there were an antimatter star out there, we wouldn't be able to tell by looking at the emission spectra, because the emission spectra should be identical to the same kind of star made of matter. Now we'd probably know it was antimatter because there's more matter than an antimatter in the universe. And if you had a giant ball of antimatter, it would be being hit by matter, and it would be giving off a ton of gamma radiation. And we just don't see that happening. But just a cool little fun fact that it is the exact same emission spectra. All right, I think that is the end. All right, I hope that this is helpful.